Let's relate now the gravitational potential and the density in a differential way, not in integral form. For that, let's take the divergence of the acceleration, and we need then to compute the divergence of the quantity that is in parentheses inside the integral. Let's again use SimPy for that. Let's define the reference frame R and the vector x in this reference frame. Now let's define another reference frame S and define the x prime, which is a reference frame that has bases that are from this reference frame, but the vectors x, y, and z are of the reference frame R. Let's define the modulus and finally compute the divergence. There we go. Let's have that in a variable. So what do we see here? So Rx is x, and Sx is the x prime. Same for the quantities y and z. So what we're having here is the components in x and y and z. The denominator is the modulus to the fifth power, and the last component that is -3, and the denominator is the modulus to the third power. So this expression here, if x is the r vector and x prime is the s vector, this is what the gradient is. Now we can see that when x prime is different than x, then the denominators are non-zero and the expression cancels out, because you're going to have that the numerator here is x prime minus x squared. So the modulus of x prime minus x squared, the square is going to cut to the fifth power, is going to have a cube, and then the two terms are cancel out and going to be equal to 0. And indeed, if we simplify the expression that we found in SimPy, take this expression different and then simplify this, you find 0. So this is the divergence of the gravitational potential, and this quantity here is 0, except when x is equal to x prime. That means that any contribution to the divergence of the gravitational field must come from the point x equal to x prime. We can integrate then in a very small region, say of radius h around this point x, and we can make h as small as we want. And when h is sufficiently small, the density is constant in this sphere of radius h, and we can remove the density from the integral. This is the expression I have done. We'll remove the density from the integral, and we are integrating only on a very small region where the modulus is less than a quantity h, and we can make this h be as small as we want. So we have a divergent here and an integration in volume. We can apply Gauss' theorem, except that the gradient is in x and the integration is in x prime. But since we can make h as small as possible, let's make it infinitesimal. So x prime is essentially minus x. That means that if we're taking the gradient in x, it is equivalent to taking the gradient in minus x prime. And then we can have this expression here that only changed in the fact that before we had the gradient in x, and now we're having the gradient in x prime. And then we have the negative sign here because we flipped this. Now we can apply Gauss' theorem and remove the divergent. By applying Gauss' theorem, we change it from a volume integral to a surface integral and remove the divergence. We also substituted here the modulus by the quantity h. Since now this quantity is equal to h, it's on the surface of the sphere of radius h that we are doing this integral. Now, to do this integral, we realize that the area element, a, which is the integral of this infinitesimal of area, it's on the surface of a sphere of radius r, and therefore it is related to the solid angle omega. For the infinitesimals then, what we have is that the modulus of this infinitesimal of area is h squared. We substitute the radius here by h, d omega. To keep it vectorial, we substitute h by the modulus of x prime minus x, and thus the vectorial of the infinitesimal is x prime vector minus x vector times h times d omega. The integral then becomes, or we cancel this h with the h cube here, becoming h squared. Now this can simplify further because x prime minus x in modulus is h. So here we have h squared is going to cancel with this h. So we have a simpler expression for the divergence of the gravitational potential. Simply then the integral of the omega, and the integral of the omega is 4 pi. So in the end, this is what we have. The divergence of the gravitational potential is minus 4 pi g rho. And now if you finally substitute the gravitational potential by minus the gradient of the potential, you obtain the Poisson equation that relates the potential and the density.